We are ready now to begin a new section, a new chapter in our lives, even. We're beginning the study of the theory of computation. Again, remember, when we talk about a theory, we don't mean some wondering about something that might be. We mean a formalized framework to discuss something. And what we want to discuss now is computation itself, the very act of using a computer to solve a problem. We have to remember that when we think of computation, we don't just think of it in terms of numbers. We don't think of it just in terms of computing a square root or multiplying quickly. We think of it in terms of the processing of languages. We write our computer code and then we want the computer to interpret it and process it and do the things that we have asked it to do. So the theory of computation begins with the study of formal languages. Just like we had formal logic, we are now going to discuss formal languages. And we don't mean C or C++ or Ada. What we mean is something a little different than that, something very mathematical. We can represent these programming languages that we know and love with formal languages. And there are formal ways to present our programming languages. But we're not going to get into that here. What we're going to talk about is what is a language. Because computation has two pieces to it. It has the language and it has the computer. And we're going to have to formalize notions of both of those things. Connect this back to the formal logic. We wanted to discuss the structure of argument. So we had to come up with formal ways to do that. I keep using the word formal, but it's the word that we have for this. So let's look at this problem here. Suppose the input strings to a program must be strings over the alphabet AB. Remember from your prerequisite course that a language, in a sense, is a set of strings over an alphabet, right? We just have a set of elements, and we call this set the alphabet. And strings are just any combination of A and B here in this case. So a language over this alphabet simply means any string formed of A's and B's in any combination. But we want the program to accept not any words in this alphabet. We only want it to accept certain ones. This is just like when we write a computer program and we can't just type anything we want. The compiler only accepts certain inputs. So in this case, we are formalizing what those inputs should be. In this case, we have to have one substring of BB. So this is the form that these strings have to take. Anything and then a BB and then anything. Where X and Y are just any strings over A and B. They don't have the BB because we have to have exactly one BB. So we want to talk about how to do this and how to discuss this in a mathematical way. So let's look at this example. Here's an alphabet. Then we can say these languages are some of the regular languages over this alphabet. And we don't just want to talk about any old language. We want to talk about a particular kind of language called the regular languages. They satisfy these kinds of properties up here. And again, I'm putting this up here so that the mathematics can just seep through the computer into your brain here by seeing this for the 12 minutes that this video will take. You don't really, we're not going to prove theorems with this in this section. This is the empty set, so of course we always have to start with that exception, the trivially true case. And this lambda here represents the null string. So this is a little awkward to talk about the set containing the null string as different than the empty set. The mathematicians they build numbers out of the empty set and then the set containing the empty set and then the set containing the set containing the empty set and whatever. So it's a lot of nothing, but it's different ways to say nothing and they're actually distinct entities. A itself, the singletons, are regular languages, and then if you have regular languages, then you can build them up this way. You can union them, you can multiply them, the product, and then we have this closure operation we'll talk about. So this just means we repeat the thing over and over again. So again, example, here are some example of the languages. So you've got the empty set, you have this lambda. We're going to see this lambda a bunch of times. It'll be more clear in context how it is used. We have the singletons and then all combinations of these things. So we've got the A and B, right, just after each other. That's what the union would be. And then we have the A and B together, concatenated in a single string. That represents the multiplication of the product here. And then A star, which would just be A repeated any number of times. So we've got all these different types of things. Okay. All right. We can also then talk about regular expressions. This is a mathematical way then to work with the regular languages. You may have worked with regular expressions before, or regexes, maybe you called them. Different programming languages have ways to deal with these things, because anytime you want to process text, maybe you want to write a web crawler that's going to look for particular email addresses or particular HTML code. You want to interpret the code that you're reading in a particular form. And so you would define a regular expression that would represent the text that you're targeting with your program. And these regular expressions are algebraic ways to represent our languages. So again, we start off with these as regular expressions. Basically, we just drop all the set notation, and now we have algebraic elements here. So again, the text goes into great depth on a lot of mathematics behind all of this that we're not going to get into. Basically, if you have regular expressions, then you can add them together, you can multiply them, and then you can just repeat them. So for an example, here's the same thing. Here's how those languages that we saw on the previous page are represented as expressions instead, regular expressions. And we are most often going to be interacting with our languages in the regular expression form. So this is how we're typically going to see them. And we're going to get really used to what a regular expression looks like. And I'll tell you that this has application beyond the limits of theory of computation. Anytime in any program that you want to work with languages, that you want to work with text that's interpreted in a particular way. Compiler writers, right? This is needed for compilers, right? You take a compiler class, you're going to repeat all of this information in the first few weeks of that class, because this is the way that we identify languages in computer science. The regular expressions represent the regular languages. We think in terms of the expressions to process our languages. So here's an example, AB plus A star. This is a regular expression. It represents this language, and it looks basically like this. So it's AB. It's just the empty string, pretty much always. We can just have A, we can have AA, and then we can have all combinations of A's. So this plus here means or. So this means we can have the string AB, which is this one, or we can have any strings that have any number of A's in them, which is all of these things over here. Right, we always get the lambda, but then this here represents AB together, concatenated as a single word, and then or A star. So we have all of these different things for our language. This one means we have A or B repeated as many times as we want, which ends up looking like this. So you can do some problems here. You can ask questions. Find a regular expression for this particular language, which would be an A followed by N B's, unioned with B followed by N A's. In this case, it's just A with B star or B with A star. So this translation is really important to think about and understand. That this star represents an arbitrary number of a particular letter of the alphabet that occurs here. So when I have the A, B star, it means that I have just any number of B's that I want. And B, A star means I have any number of A's, and then the plus sign is interpreted in or here, just like it does in Boolean algebra. Use a sentence to describe this language. Now we want to be able to express this language in terms of English. We're well used to doing that. So what we can say here is the strings over AB whose substrings of A have length 1. So basically what we're saying is that we can have B any number of times, or we can have AB any number of times. And what this does is this means that if you look at this carefully, you can't ever have two A's in a row, because you can have B, 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 B as many times as you want. You can have A, B, A, B, A, B as many times as you want, but there's no way to combine these to get a single A that is not, that's two A's. There's no way to combine these to get two A's that are in a row. Every single time you do this, you have to have just the singleton A. And then this just tells us that you can end with an A as well, right? This means that we have to end with a B. This portion of the regular expression says that we have to end with a B. And then this piece over here says that I can have an A as my final element as well. The lambda means I might end with a B. If we pick the lambda for this second portion, that means I can end with a B. So the string AB would just be two applications of this and then end with the lambda. Whereas ABA would be a single application of this and then choosing the A to end it. There's a bunch of examples of this in the text. Run through it, make sure you get it. So back to this problem here, we want to have exactly one substring of BB. This is what we're after. So we can just say that X is this and Y is this. So what we're doing here is making sure that we don't have two B's together. So in this one, we can have any number of A's in either one that we want, and then BA. So this is the same structure that we just saw. What we want to do is make sure that we have no double B's. And here on the Y, we can't start with the B. On the X, we can't end with the B, and on the Y, we can't start with the B. Yeah, because in between this is going to be BB. We want this to be X, BB, Y. This is the structure over here, X, BB, Y. And so what we want is we're going to have two B's following the X. And if we allowed X to end with a B, we would have three B's in a row potentially. And we don't want that. So X is going to be the regular expression of this form. Y is going to be a regular expression of this form. So you just put BB in between these and multiply the whole thing together. And you get something that looks relatively complex, but it's a regular expression that represents this relatively simple English statement. We contain exactly one BB substring. But to then render that in the formal language of regular languages it takes a little bit of algebra to do. Our intellectual development that has come with working with the first order and a predicate calculus should place us in a position where we can see this pretty quickly. I'm going to end with this, just throwing this out there with a word that we're not going to be doing algebra like this. There's a ton of problems. I could just throw problem after problem after problem at you that's doing all of this algebra. And while that is fun and while that is rewarding, it's not what this class is about. So I just want you to end here understanding that all these regular expressions, they didn't just fall out of the air. They weren't something that we just looked under a rock and found. These are something that mathematicians have developed in a particular way. You might notice in the textbook that we've skipped the chapter on actual algebra, right? Algebraic structures. There's an entire mathematics course called Algebraic Structures to talk about what is an algebra. So this section here actually follows a discussion of what algebras are. And we didn't do that because this is not an algebraic structures course. So we're not going to look at this through that lens. But I'm going to throw it out here because it's math, and math is awesome.